Okay, so hello everyone. Welcome to LICD lecture 41E. Today we are going to discuss four topics explicitly. These are very important topics related to analog filter design. So the first one is second order active KRC low pass filter. So we will do the analysis, then we'll derive the transfer function, then we'll build up the frequency response and LT spice simulation followed by it. Then next we will derive the expression for the generalized transfer function, find out the frequency of f0 and quality factor for second order low pass filter. Next is we will design a second order KRC low pass filter using equal component design, and lastly we will design the second order KRC low pass filter using unity gain design. So these are the four topics which we will be covering in today's lecture. So let us start. Okay, so first topic for today is KRC filters or Salin K filters, named after its inventor. Okay, so KRC filters are also called as RC filters with a gain K. Okay, so we will discuss the second order low pass KRC active filter. So this is my Opamp which is connected in the non-inverting mode. Hence, the gain of the Opamp is 1 plus RA upon RB, which is a constant. And over here, if you remember, in the first order filter, we have only one RC element, R1 and C. Here we have two RC elements. So basically, it will be a second order filter. So here only one difference is the capacitor C1, instead of ground, it is connected to the output back. Okay. You have back-to-back two RC elements. First RC element, the register side of it is connected to Vin, and the second RC element together with the first one are connected to the non-inverting terminal of my op-amp. Okay, so let us begin with the analysis. So over here, it is acting as a low pass filter, right? So let's say f0 is my cutoff frequency. So for frequencies f which is lesser than f0, let me see if we have a, yeah, we have that diagram. I have to divide the screen into two parts. Okay, let me open the second PDF also. I'll keep the diagram open over here. The frequency plot, basically. Yeah. So now it's better. So here, let me just reduce the little bit font. Yeah. So for frequencies f less than f0, that is in the low frequency range, your reactance offered by the both the capacitance are very high. So at low frequency range, reactance offered by C1 and C2 is very high because frequency is very low. Hence, both of them will act as an open circuit. So what will happen due to that? So all the input applied voltage will be appearing at the output. Since both the capacitors will be behaving as open circuit at low frequencies, so op-amp V in over here will reach the inverting terminal, and this circuit will act as a non-inverting amplifier, which amplifies with a gain of K, where K is given by 1 plus RA upon RB. This happens only at low frequency. So at low frequencies, capacitor C1 and C2 behaves as open circuit, and this is a simple non-inverting amplifier case with a constant gain, 1 plus RA upon RB. Now, next. So for at low frequencies, circuit allows the frequencies below f0 with maximum gain, K equal to HOLP. Okay. Next part, as the input signal frequency increases above f0, what will happen is in the high frequency range, the reactance offered by both the capacitors goes on reducing, correct? So therefore, the input reaching the input reaching to the amplifier goes on reducing, so the output goes on reducing. Okay, so that means only one thing, that the circuit will attenuate the frequencies after f0. So that behavior we have already observed in the first order low pass filter. Similar thing will happen over here. So thus the circuit will behave as a low pass filter, and for f greater than f0, it will attenuate the signal at the rate of minus 40 dB per decade. Now, last time in the first order filter, we said that the roll off rate is minus 20 dB per decade. So here it will be minus 40 dB per decade. indicating it's a second order low pass filter. Now we'll see that shortly why minus 40 dB and why we call it as a second order low pass filter. So first of all, what we will do is we are trying to derive the generalized expression for the transfer function to determine the cutoff frequency and the quality factor. So over here we have replaced these elements, capacitive elements, by admittance. So y4, y1, y2, y3, y4, and we have in place of these two resistors and two capacitors. I mean that will be easier to analyze. So this is the general structure for a second order filter. I mean, it can be a low pass filter or a high pass filter, but the general structure of it, it's derived over here. Okay. So depending upon whichever elements are there in Y1, Y2, Y3, and Y4, it will become either low pass filter or a high pass filter. Right now, we are concentrating on the general transfer function. So why is the admittance? So let us begin. Let me keep that ready over here also. Okay. So let us start. So we apply KCL at V1 node. So what you will get, V1 minus V in into Y1 plus, these are outgoing currents, right? All of them are outgoing currents, plus V1 minus V2 into Y2 plus V1 minus V0 into Y3. So the third current is this V1 minus V0 into Y3. Okay, so here we are collecting the terms for V1 together. So Y1 plus Y2 plus Y3 into V1 minus V0 into Y3 minus V2 into Y2 is equal to V in into Y1. Okay, so these are the terms which we are writing. And how can we write V2 over here? V2. So basically, we know that this Opamp is operating in the non-inverting mode with the input as V2. So if the input is V2, and what will be the output of your non-inverting amplifier? It will be V out is equal to 1 plus RA upon RB into V2, correct? So we substitute over here, instead of 1 plus RA upon RB as K. So your V2 will be VO upon K, where K is 1 plus RA upon RB. I hope that this point is clear. Okay, so we'll rewrite this expression, above expression, instead of V2, we have substituted VO upon K. And here we club the terms of VO together now. So VO will contain two terms, Y2 upon K plus Y3, which is equal to Y1 into V. So this is our equation number 1. Okay. Now similarly, we apply the KCL at V2. So what it will give you? V2 minus V1 into Y2 plus V2 Y4 plus 0 is equal to 0. Okay, so all are outgoing current. So here the current entering the Opamp terminal is considered to be 0. So because the Opamp has a very high input impedance. Okay, we rearrange the terms over here. So Y2 plus Y4 into V2 will be equal to V1 into Y2. We substitute V2 as V0 upon K, and hence we can rewrite the expression of V1 in terms of V out as Y2 plus Y4 divided by K times Y2 will be into that, we will substitute equal to, just a second, yeah, so V1 will be equal to Y2 plus Y4 upon K times Y2, and this whole numerator and denominator is multiplied by V0. Okay, so these are the values. So next we substitute equation number 2 in 1. So let me show you equation number 1 over here. So this is our equation number 1. We substitute, whenever we have a V1, we substitute Y2 plus Y4 upon KY2 into V0 in place of V1. Basically, we are trying to establish V out and V in relationship. So we are eliminating V1 over here. So we got this expression now. Let me maximize it now. Okay. So you have all the terms now. So if you solve it patiently, I am not reading it out everything. So if you solve it, it will hardly take 2 minutes. So please solve it. And finally, you will get the transfer function for generalized second order filter will be H of S, which will be equal to K times Y1 Y2 divided by Y1 Y2 plus Y1 plus Y2 plus Y3 into y4 plus 1 minus k times y2 y3. So this is the generalized transfer function for a second order filter. Now let us go back over here. So for a low pass filter, y1 was, this is admittance, right? So y1 will be y1 and y2 are 1 upon r and 1 upon r2. Y1 is 1 upon r1, y2 is 1 upon r2, and y3 is c1 into s, y4 is c2 into s, sc2. Okay, so we substitute all the values in the general form. So this is my general form. Okay, here it is. So we substitute the values over here. Let me just little bit reduce it. Okay, so instead of y1 and y2, we have 1 upon r1 and 1 upon r2, and y3 we have c1 s1, sorry, sc1, and y4 we have c2. So we substitute all the values, and then we will rearrange these terms. Okay, so we are accumulating all the terms, cross multiplying, algebraically solving it, and then we'll finally get equation number 3. So I will keep this on for 5 seconds. This page you can jot it down in the on a piece of paper and derive this similarly. So finally I got the expression number 3 of h of s, which is k divided by 1 plus r1 r2 c1 c2 s square plus 1 minus k r1 c1 plus r1 c2 plus r2 c2 the whole into s. Okay, so we will compare with a standard second order transfer function for a low pass filter. Now I will tell you what is this. Let me open the one PDF. So there are standard second order transfer functions which are already available. I will show it to you all. So these are the second order responses, second order filters. So the general form will be, yeah, here it is. So basically you all can go through this text. This is explaining the standard second order responses of both high pass, low pass, all pass and band pass responses. Okay, so you all can have a look at it. So your h of s is n of s divided by s upon omega the whole square into 2 mu s upon omega naught plus 1. So this is your polynomial. N of s is the polynomial of s with a degree lesser than or equal to m equal to less than 2. Omega naught is the undamped natural frequency in radians, and zeta is the damping ratio. So if zeta is greater than 1, poles are real and negative. The system is overdamped. If zeta is between 1 and 0, the poles are complex conjugate, and yeah, they lie in the left half of the S plane. Okay, so this is the underdamped system. If zeta is equal to 0, we have undamped system, and it is a sustained undamped system. And if zeta is less than 0, the filter you have a exponential filter must have will be a stable filter basically. Okay, so the meaning of the quality factor, q is the quality factor. The meaning of the quality factor will be clear in some time from now. So what I want to say is all second order low pass filter can be put in the standard form like this. So this is the standard form of a low pass second order filter. So let's compare it with the standard form. So that is what I've written over here. This is HLP of j omega, which is given by HOLP into HLP j omega. Okay. So here we have HOLP divided by minus omega upon omega naught square plus j omega upon omega naught divided by q. So this is the generalized standard transfer function for a low pass filter. That's what I wanted to show. Now we'll continue from here on. So what we'll do is we'll compare equation number 3 and equation number 4 and find out the generalized expression for the f naught. You can find the value of f naught and q from here, comparing with the standard second order transfer function for all the low pass filters. So when we compare this equation number 3 and 4, what do we get? Let me just go back to equation number 4. Okay, I need to little bit expand it so that it is visible. Yeah, now it is fine. Yeah. So what we will do is, after comparing with the standard second order transfer function, and we can also put s equal to j omega, correct? So that we get terms in, you put s equal to j omega in equation number 3. So what you will get, k divided by, here we have s square, so your minus sign will come because j square is minus 1. So in the denominator we have 1 minus r1 r2 c1 c2 omega square plus j omega into 1 minus k into r1 c1 plus r2 c2 plus r1 c2 the whole into omega. Okay, now we actually compare equation number 4 and 5. Okay, so equation number 4 is this, you can see very clearly equation number 4. So what you will get by comparing equation number 5, so equation number 5 is this. So we can easily say that k is directly equal to HOLP, which is given by 1 plus RA upon RB. Now this is called as the passband gain of low pass filter. Now we also need to compare the second term over here, minus omega square upon omega naught square. So here we have omega square. So omega naught might be R1, R2, C1, C2. So we substitute by comparing, we get 1 upon omega naught square will be equal to R1, R2, C1, C2. Okay. So basically this is what we get. We take omega. So omega naught will be equal to 1 upon square root of 1 plus R1 C1 into R1 C1 into R2 C2. Okay, this is equation number B. So this is the cutoff frequency of a low pass filter. Now if we consider R1 is equal to R2 and C1 is equal to C2 is equal to C, then omega naught will be 1 upon RC and F naught will be the 1 upon 2 pi RC, only if R1 R2 is equal to R and C1 C2 is equal to C. Okay, now we'll equate the third term basically. So the third term was j omega upon, actually here omega is extra over here, so please pardon, here omega is extra written, so please note that error. So here j omega, omega naught upon q. Okay, 1 upon omega naught upon q is this factor, so that is what we have written over here. 1 upon omega naught q will be 1 minus k into r1 c1 plus r2 c2 plus r1 c2. Okay, so where omega naught is 1 upon square root of r1 r2 c1 c2. So q will be given by 1 upon 1 minus k square root of r1 c1 upon r2 c2 plus square root of r2 c2 upon r1 c1 plus square root of r1 c2 into divided by r2 c1. So this is my equation for my quality factor. Okay, so if we consider R1 is equal to R2 is equal to R and C1 is equal to C2 is equal to C, all these factors will get cancelled out. I mean, it will be a factor of 1. So the Q quality factor will be 1 divided by 1 minus K into square root of 1 plus square root of 2 or plus square root of 1 plus square root of 1. So basically we can add these 1, 1, 1 together. So you will get Q is equal to 1 upon 3 minus K. So this is the quality factor. If we select R1, R2 is equal to R and C1, C2 is equal to C, and 1 upon quality factor will give us the damping ratio for a low pass filter. So alpha is equal to 3 minus K. So the value of the damping ratio for a low pass filter can be determined by choosing the value of K basically. Okay. So where Q is the quality factor which is given by 1 upon 3 minus K. Okay. So that's what we get. So we see that from these equations A, B, and C. So these are my equations. A is HOLP, equation B is omega naught, and C is over here Q. So we observe that K and Q, K basically, where is K over here? Yeah, K expression for K is dependent upon component ratios, correct? Whereas omega naught depends upon the component products. That means R1 into R2 into C1 and C2. Whereas Q also depends upon the component ratios, as you can see. So K and Q depend upon the component ratios, the R and C ratios, and omega naught depends upon the component product, that is R and C product. So because of the component tolerance and the Opamp non-idealities, the parameters of an actual filter are likely to depart from their intended values. So over here, since we have 5 parameters, but only 3 equations. We have a choice of fixing the 2, and we can specify the design equation for the remaining 3. Okay, so here we have it 5 parameters, that is K, R1, C1, R2, and C2. But we have only 3 equations, right? A, B, and C. So we have a choice to fix 2 parameters, and then we will specify the design equation for the remaining 3. So there are 2 common approaches over here. We have 2 common designs which are called as equal component design, and second one is unity gate design. So we will see them one by one now. I hope that you all don't have any doubts. So what is equal component design? Equal component design means imposing, as we have already used, R1 equal to R2 equal to R, C1 is equal to C2 is equal to C. That simplifies all the expressions. So HOLP will become K, omega naught will become 1 upon RC. That means F naught will become 1 upon 2 pi RC. Your Q is 1 upon 3 minus K, and your HOLP is K, which is 1 plus RA upon RB. Okay, so advantage of using equal component design is we can tune the cutoff frequency and the quality factor independently. So as you can see, the cutoff frequency is dependent upon RC elements, and Q is dependent upon RA and RB. So they are independent. So we can adjust or tune them independently. So this is the advantage of equal component design. Now, the disadvantage of equal component design is, its name is equal component design, right? Yeah, equal component design. The disadvantage is at the high value of quality factor, the equal component design becomes too sensitive to the tolerance of RA and RB. So when the ratio is very close to 1, if K is such that it is close to 3, that means RA upon RB reaches 2, the Q will become try to go to infinite or even negative, which will cause the filter to oscillate. So for these reasons, KRC filters are used for quality factor lesser than 10. Okay. So just because you see carefully in the expression of Q, we have 1 upon 3 minus K. So somehow if K becomes 3, Q will become infinite, right? So you need, if somehow the ratio RA upon RB should never reach 2, okay, or even surpass the value of 2. We have to take care of it, or a quality factor will become negative, or it will even become very, very high. So hence, for these reasons, KRC filters are used for quality factor lesser than 10. Okay, so we have come to a very first design. So using the equal component design, design a second order KRC low pass filter with a cutoff frequency of 1 kilohertz and a quality factor of 5. Also find its DC gain. Okay, so for a second order low pass filter using equal component design, we select R1 equal to R2 equal to R, and C1 equal to C2 is equal to C. Hence, the formula for cutoff frequency will be 1 upon 2 pi RC, which is 1 kilo ohm. So we select the value of C as 10 nanofarad. So the value of R will be 15.91 kilohertz, kilo ohms. Actually, here I am written again a mistake, kilo ohms. So we select the standard value of 15 kilo ohms over here, right? Now, they have given the quality factor of 5. So we can equate Q is equal to 5, and Q is given by 1 upon 3 minus K, where K will be evaluated now. So K will be 3 minus 1 upon 2, which is 2.8. So K is 2.8 basically. So how we derive this? So Q is 1 upon 3 minus K. So K will be 3 minus 1 upon Q. Okay, so that's what we have written over here. 3 minus 1 upon Q, which is 5. So K will be 2.8 now. So now we can easily design the values of RA and RB. So RA upon RB will be 1.8. So let RB will be equal to 10K standard. So RA will be equal to 18K standard. Okay. Now the DC gain. Now what is the DC gain? DC gain meaning your K. So K is given as 2.8. So 2.8 is my DC gain. If you want to convert that into a dB, you can substitute 20 log to the base 10 of 2.8. That's the value which you will get. Okay. So this is your design circuit. So this is my design of second order KRC low pass filter using equal component design. As you can see, RA value is 18K, RB value is 10K, R1 and R2 is 15K, C1 and C2 is around 10 nanofarad. Okay, so this is the design of a second order low pass filter. Okay, now what we will do is we'll check its simulation in LT-Spice. Yeah. So let me open up LT-Spice, and let me open the circuit now. This is 41B. Yeah, equal component design. Okay, so these are the values which we have got. RA, RB. Let us check that now. Okay, so the values are as follows. RA was 18K, RB was 10K, R2 and R1 we have substituted the values which we have calculated, not the standard values, because in LT Spice we can select any value of register values. But when you do it on the breadboard, see to it that you take the nearest standard value close to 15K. Okay, so C1 and C2 are given as 10 nanofarad, and now let's check its frequency response. Okay, so this is my frequency response of the filter. Fine. So here the gain, the passband gain will be 20 log to the base 10 of 2.8. So that comes out to be 8.94. Let's check that. Yeah, 8.94. I'm getting it theoretically, and practically we are getting a value of 8.95 dB. So this is my passband gain, and here we have a slight up this nature, and then it is going down. So we have to check the cutoff frequency at this nature only. So here at this value. Okay, so this will be like how much it is. Let us check. So we have designed for, what was it, was designed for 1 kilohertz, right? So you will get this 1 kilohertz at the highest peak over here. As you can see, its value is 1.01 kilohertz. We have designed it for around, normally we take it 3 dB down, but in case of this second order filters, there will be a slight deviation because the quality factor is 5, Q is 5, there will be a slight up is nature, and then it will settle down to below values. So here the highest peak over here is my cutoff frequency, which is 1 kilohertz. Okay, and this we told that the roll off rate is around 40 dB per decade. So let's check that out. So at 0 dB, it was, the frequency was around 2K, and at minus 40 dB, it's around 200. Okay, so it's around approximately equal to minus 40 dB per decade. So roll off rate is minus 40 dB per decade. Okay, now we have completed this equal component design. So this was the passband gain, 20 log to the base 10 of 2.8, 8.94 dB, and this was the cutoff frequency, the highest peak over here. Okay, don't worry, we will make you understand why this is the, why we measure at this value over here in the next class. So the second technique is the unity gain design. So unity gain design is making k equal to 1. So when we make k equal to 1, that means we have designed Opamp as a buffer, not a non-inverting amplifier. Correct? So we will make a non-inverting amplifier as a buffer without RA and RB. So if we don't have RA and RB in the circuit, that becomes a unity gate design. That means K is equal to 1. So when K is equal to 1, HOLP is equal to 1, right? So these are the design steps to simplify the math, and we are relabeling the components. So R2 will be equal to R, C2 will be equal to C, so R1 will be equal to M times R, and C1 will be equal to N times C. Okay, so these are the standard steps which you have to follow. So omega naught will be 1 upon square root of Mn into Rc, and Q will be equal to square root of Mn divided by M plus 1. Now, these are all the design values. So for a given value of N, Q is maximized when M is equal to 1. Okay, that is, M is equal to 1 means what? All the resistors are same. So that becomes your, the design will be equal component design then. So, but over here is for N equal to, for a given N, right? Q will be maximized when M is equal to 1. Okay, that's we have to take care. When all the resistance are equal. When M is equal to 1, all the resistance are equal. When N is equal to 1, all the capacitors are equal. Okay, so with M equal to 1, will give the form, will give in terms of N. So you take the bracket, you just take the square on both the sides, so it will be Q square into M minus M plus 1, so that will be 4Q square, right? and that will be equal to root of n, correct? So that will be equal to m into n. So m is equal to 1. So n is equal to 4q square. So in practice, we take n is greater than or equal to 4q square. Okay. I hope that this point is clear. So m can be found out by this relation. M is equal to k plus square root of k square minus 1, where k is given by n upon 2q square minus 1. So these are some tedious design steps, but we have to follow them for a proper unity gain design. So again, I repeat the steps. Unity gain design, we make k equal to 1. That means instead of a non-inverting amplifier, we use a buffer without RA and RB. Okay. So this will maximize the bandwidth. Now, why we do this? It will minimize the number of components. Also, it will maximize the bandwidth of the op-amp. So if you impose the gain as 1, you will have a much higher bandwidth as compared to equal component design values. Okay. So here k is 1, HOLP is 1. We relabel the component values. So R2 is R, R1 is M times R, C2 is C, C1 is N times C, omega naught is 1 upon square root of Mn into R into C, Q is square root of Mn upon M plus 1, and M equal to 1 gives N equal to 4Q square. In practice we take N greater than or equal to 4Q square, and M can be found out as M is equal to K plus uh, square root of K square minus 1. So this is your value of K. K is what? No, this is small k actually, not that particular k. This is different. This k is different. This is the passband gain, and this k is different. Okay, where k can be found out as n upon 2q square minus 1. So these are all the design steps for a unity gain design. So disadvantage is we cannot independently tune cutoff frequency and quality factor. Okay, so here the cutoff frequency is given by omega naught, which is also given by M and N elements, and your quality factor also has M and N. So your quality factor and your cutoff frequency are related to each other. They are not independent. So that's the only limitation of unity gain design. Unity gain design. So let us begin with one of the design. So we need to design a unity gain, using unity gain design. Design a second order KRC low pass filter with a cutoff frequency of 10 kilohertz and a quality factor of 2. Okay. Now, for a for a gain of for a unity gain design, k is 1, that means HOLP is 1. So the circuit is given as like this. You see over here there is no RA and RB. Okay, we have a unity gain buffer like a voltage follower. So we only have RC elements. So two RC elements are R1, R2, C1, C2. So that's how we do the design, and that's how the circuit will look like. Now the first step is making relabeling the parameters over here, the components, that is R2 is R, so R1 will be M times R, C2 is C, so C1 will be N times C. So we assume the value of C as 1 nanofarad, and the value of N will be greater than or equal to 4Q square. Q is given as 2, so it will be 4 into 4, 16. So let N equal to 20. Okay, if C2 is equal to 1 nanofarad, so C1 is N times C2. So it will be 20 nanofarad. C1 will be 20 nanofarad. Let's find the value of K. K will be N upon 2Q square minus 1. N is given as, and we have calculated it as 20, and 2 is 2. So this K value will be 1.5. So what will be the value of M? M value will be K plus square root of K square minus 1. Okay, so that number, if you substitute in your calculator, you will get a number of 2.618. So please cross check this number. Now we have the value of N, you have the value of M. So everything we have. So here F naught is equal to square root of Mn into 2 pi RC. So C we already calculated. The C value is around 1 nanofarad. Correct? C value is 1 nanofarad. Yeah, C value is 1 nanofarad. So we substitute over here 1 nanofarad. F naught is 10K, and M and N values are 2.618 and 20. So with this, we calculate the value of R, which comes out to be 2.199. That is 2.2K standard value we select. Okay. So MR will be 5.758. So 5.758. We substitute the standard value as 6.2K near a standard value. Okay, so so this is my design. This is my second order KRC low pass filter with using unity gain design with f naught equal to 10 kilohertz and Q is equal to 2. So R1, R2 is 6.2, 6.2 kilo ohms, C1 is 20 nanofarad, and C2 is 1 nanofarad. So this is the design. Now let's check this design in LT Spice. So this was equal component design. So there are two techniques basically. The second one is the unity gain design. So as you can see over here, I have taken the values which are quite close over here. So R1 value was R2 value is R, R2 value, let's check. So this is R, right? So over here, R2 is R, right? So this is 2.2K. R2 is 2.2K. And what is R1 M times R, which is around 5.758. So we have substituted that value only over here. C1 was here the design, this R2 should be 2.2 instead of 6.2. That's the mistake we have done, but we have corrected that in the LT Spice. So C1 is 1 nanofarad and C2 is 20 nanofarad. Now let's check the design. It is designed for cutoff frequency of 100 kilohertz and quality factor of 2. Let's check that now. Here the passband gain is around 1. So you will get a 0 dB over here, passband gain. So yes, the passband gain is 0 dB. Now let's check the cutoff frequency. So cutoff frequency will be at the highest peak over here. Okay, so here is my cutoff frequency around 10 kilohertz. I'm getting this value at the highest peak. And then afterwards it falls at a 20 dB per decade. Okay, I hope that this point is clarified now. Okay, so this was the design for second order low pass filter using unity gain design, where f0 was 10K as it was coming and quality factor was 2. Okay, so that's how you proceed with the design for a unity gain design equations. Okay, next, okay, this is what we have done. So this f0 was 1 kilohertz, and that's the frequency response for a KRC low pass filter, second order low pass filter using unity gain design. Okay, next we also see another design. So design a second order low pass Butterworth filter with a 3 dB frequency of 1 kilohertz. Okay, so here they have given Butterworth filter. Now Butterworth filter I will be describing it in the next lecture. So Butterworth filter, you just remember the quality factor for a Butterworth filter will be around 0.707. So only this much you need to remember, rest steps are same. So we are free to choose any design. So normally equal component design is easier to do. So we'll adopt that approach. If the design technique is not mentioned, we can go for a equal component design. If the design technique is mentioned that you have to do it with a unity gain design, that then you have to follow that approach. Okay, so let's start. So we'll adopt the equal component design approach, wherein we have R1 equal to R2 equal to R, C1 equal to C2 is equal to C, and this is my circuit, RA, RB, R1, R2, and C1, C2. Okay, so only thing is for Butterworth frequency response or a filter response, the quality factor Q is 0.707. Okay, that's the only thing. So f0 is 1 kilohertz, so 1 upon 2 pi RC. So let's substitute the value of C as 10 nanofarad. So C1, C2 will be 10 nanofarad. So we calculate the value of R. R came out to be 15.91 kilo ohms. So we select the standard value as R1, R2 is equal to R is equal to 15 kilo ohms. Okay. Now the quality factor Q is given as 0.707 because it is a Butterworth frequency response, which is equal to 1 upon 3 minus K. So K will be 3 minus 1 upon Q. So that number will come out to be 1.585. That means K is equal to 1. RA upon RB, which is equal to 1.585. So RA is 0.585 times RB. So let's select the value of RB as 10K. So RA will be 5.85 kilo ohms, which is the nearest standard value 6.2 kilo ohms. So in this way, we designed the filter that is a second order KRC low pass Butterworth response filter. So here RA, RB values are different. There RA is 6.2 kilo ohms, RB is 10 kilo ohms. R1 and R2 are 15 kilo ohm standard values, and C1 and C2 are 10 nanofarad. So let's check this design in LT Spice, and that will complete today's lecture then. Let me delete this, and let me open the Butterworth equal component design. So this is the design circuit for your schematic for your second order KRC Butterworth low pass filter using equal component design. So here we acquire the F naught to be 10 kilohertz with a quality factor 0.707. Okay, let's simulate this circuit. Okay, as you can see that if the quality factor here it is coming perfectly well, there is no glitch as it was coming earlier with the quality factor of 5 and 2. So it's a perfectly like a frequency response. And here the here your passband gain. Let me show it to you. What will be your passband gain over here? A is 1.585. So one of you, if you can take log of 20 log of 1.585 and tell me the answer. So that answer will be 4 dB. So if you convert this, this is actually your HOLP. So this HOLP is nothing but your K is nothing but your gain of your non-inverting amplifier, which will be which is calculated as 1.585. So what you do is you take 20 log to the base 10 of 1.585, that will be 4 dB. So your passband gain should be 4 dB. Let's check that value. Yeah, as you can see clearly, it's coming out to be 4 dB, 4.0005693 dB. Okay, now how we'll check the cutoff frequency? Cutoff frequency will be 3 dB down, meaning it around 1 dB you should get the cutoff frequency. So that is the value which we are getting over here, very close. So around 1 dB over here we can see 3 dB down, right? So from 4 dB, 3 dB if you cut, you will get 1 dB. So around 1 dB, you are getting the frequency as 998 hertz. We have designed it for 1000 hertz, but we are getting 998.17 hertz. That's quite close. And the Butterworth response is the smoothest response. So the transition from the stop band to the pass band is very, very smooth. So the frequency is below, if not equal to 1 kilohertz, all the frequencies are passing. That's a low pass filter. And the frequencies above 1 kilohertz, all the frequencies are getting rejected at the rate of 20 dB per decade. So let's check this value. Here the at around 7 dB. Let's check this around minus 7 dB. You're getting 1.86 kilohertz, and around 47 dB, right? No, it's not 47. So around 47 dB. Okay, yeah, around 47 dB you're getting 18 point something. So around with a 10 decade change in frequency, the gain is falling by 40 dB per decade. So you can easily check this value. If I can place one cursor over here and verify these numbers. So here it is. Here the frequency is 2 kilohertz and the gain is you know 8 minus 8.3. So let's check at 20 kilohertz now. So this is around 20 kilohertz. So you can see the subtraction of both, it's around close to 40 dB. Okay, and the frequency increase, it's from 2 kilohertz to 20 kilohertz. So that proves the point. The roll off rate of this second order low pass filter is around 40 dB per decade. So basically, if the quality factor is around 0.707, you get a very flat response. As you can see, the transition from the pass band to the stop band is very, very smooth. Whereas in case of earlier designs, it was not the case, as you have already seen. Okay, so yeah, this completes the design. So we get a very smooth response with a passband gain of 4 dB and the roll off rate of minus 40 dB per decade, and the frequency cutoff frequency was 1 kilohertz. You see over here in the previous designs, let me show it to you. You were getting this small, there was not a smooth transition, it was like a small glitch, and the F naught was coming out to be in the highest peak. Whereas in case of a butterworth response, which is a flat response, right, very smooth response transition from pass band to stop band, we are getting a perfect second order low pass filter response. Okay, so I think that's it for today's lecture. We have completed the generalized derivation, the concept of a second order KRC filters. So KRC filters are nothing but RC filters with a gain of K, and then we have derived the generalized transfer function. We have compared with the standard form of the transfer function. Let me just show it to you. Yeah, so these are the objectives which we have met, and then we've gone to the design of a second order KRC low pass filter using equal component technique and using unity gain design. And also at the last, we have designed a second order KRC filter with an equal component design, but for a butterworth response, butterworth frequency response. Okay, so I think that's it for today's lecture. Next time we'll start with the high frequency second order high pass filter frequency response. So until then, have a good day and thank you.